I searched for the source of this wallpaper that I'm having right on both Yandex and Google. To be honest, Yandex wasn't of much help, but Google's AI said the following: based on visual evidence, the image captures a view from a car approaching the Manhattan skyline in New York City. The prominent skyscraper is part of the evolving Skyline Hill Financial District. To be honest, this looks a bit Eastern European to me, but if the AI says it's New York, I'm gonna trust them blindly. We should trust our new overlords from now on. All right, so these two images are actually taken on the Brooklyn Bridge, and now when I look at it, it does look similar, but it's not similar. The lampposts are all different, and this building right here, I mean, it's blurry. It's blurry in the background. God knows if it is the same one. By the way, if you know where this image has been taken, please enlighten me. So, plan for today's episode is to go through a book on machine learning, and it seems like it's a pretty simple book. It's called the 100-page machine learning book, and it contains a bit more than 100 pages. It actually contains 160 pages. I still wouldn't consider it fake advertisement, though. 160 is still 100. Even though it's closer to 200, but what can you say? So my plan is go through the book, see if I can finish it in 2, 3, 4 sessions. I don't know much about machine learning. I tried to go through a machine learning textbook once. I failed miserably. I think you can see that on this channel. If you are interested in seeing how someone who is a layman and debutant does this, please stay and enjoy the video. Here we are. I'm gonna skip all the introductions. I'm gonna skip the prefaces. We're gonna get straight into the work. By the way, the author of this book, Andrei Burkov, actually sells the books and distributes it in the read first, buy later manner and principle. So if you like it, please do buy it and help the author as well. All right, let's start it. Okay, I will use the mind map way of referencing and taking my notes. Basically, from the center of the big topic, I'm gonna pull out important concepts and things that are interesting. First of all, what's machine learning? Machine learning is a subfield of computer science which is related to building algorithms. And those algorithms, in order to be useful, they rely on a collection of examples of some phenomenon, either from nature, from humans, or from another algorithm. Another way of defining machine learning is solving a problem by gathering a data set and then building an algorithm based on that data set. And this algorithm is building a statistical model that somehow will be used to solve the practical problem. I'm going to use this second definition right here because the first one seems a bit esoteric in nature. So what's machine learning? Basically, it's a data set plus an algorithm that builds a model based on this data set. All right. We have 4 types of learning: supervised, semi-supervised, unsupervised, and reinforcement learning. So what do each of these types of learning do? Supervised learning. And it says here, in supervised learning, the data set is the collector of labeled examples. Each element xi among n is called a feature vector. All right, so this needs to be simplified a bit for my own understanding. All right, so the big picture in relation to supervised learning is, I'm giving you examples with correct answers. Learn the pattern of correct answers so you can predict the answer for new examples, basically. And there is this scary math right here. So this just means we have n examples, and each example has the input, which are the features, and the correct answer, which is the label. So every data point will look something like this. X1, Y1, X2, Y2, bum bum bum, all the way to Xn, Yn. Each element, xi, is called a feature vector. A feature vector is just a list of numbers that describe one example. It's as simple as a row in a spreadsheet. And if one row might look like this, and this could be the height, this could be the weight, this could be the age, this could be the gender, and I can write here 75, 70, 30, and the gender is 1. Now this is the simplified definition. A bit more complex one from the book is saying a feature vector is a vector in which each dimension, y, equals 1 to d, contains a value that describes the example somehow. And this value is called a feature and is denoted as xy. Okay. And this row right here might look something like this. I can have x is equal to 175, 70, 30, and 1 right here. Now, what's a feature? Each position in this vector is called a feature. And the book is denoting these features as x and y is on top. I don't know how you denote this. The feature in the position y. All right. So x of 1 would be the height, x of 2 would be the weight, x of 3 would be the age, and x of 4 would be the gender here. And each position always means the same thing. If column 2 is weight for one person, it must be weight for all people, which is very important. Otherwise, the model would be confused. All right. What is this then? Y, I. This just means that this is the correct answer for this example. And we have two main types of solutions. And the two main types here are classification or categories. If y belongs to a finite set of class sets, it means that it's a classification. Basically, we can have, and this is one of the most common used examples, a spam detection. We can have only two classes, that something is spam or not spam. Email 1 could be spam, email 2 could be not spam, and so on and so on. Or in similar fashion, cancer detection. We can have two classes, cancer and no cancer. Now, we also have regression. regression deals with real numbers. If the y is a real number, it's a regressive algorithm. Basically, we can get something like this as a solution, 350,000 whatever dollars or euros, and we can use this to predict house prices or predict temperature. And the goal of this is to produce a model that takes x as an input and outputs information, allowing us to deduce y. In even simpler words, we want just to learn a function. A function saying f of x equals y. And we give the model the input. And these are the inputs right here. This whole data set is the input. And we provide it to this function. And it can output something like 0.782. And it can say, okay, it's an 82 probability that this email is spam. It's an 82 probability that this person has cancer, unfortunately. So instead of memorizing answers, it learns patterns like, okay, if someone has, so, I don't know how to say this nice. If someone is obese, if someone is fat, and if someone is old, these two factors might contribute to a higher chance of cancer. Of course, not only these two factors. In a real data set, we would have thousands. Okay, maybe not thousands, I'm overreacting, but we should at least have a couple of dozens information, including, I don't know, family history of illnesses, smoking status, work environments, a lot of factors that could contribute to the final score. Basically, supervised learning is like if you give a child a bunch of pictures of dogs and cats, and we have each picture labeled correctly, we are expecting the child, after seeing a lot of examples, to learn, oh, a dog usually, okay, I drew this completely wrong, but okay, a dog, how does this look like if I zoom out? A dog usually looks like this. A cat usually looks like this. Then you show a new picture and they say, oh, that's a dog, that's a cat, and so on and so on. And why it's called supervised? Because the algorithm is supervised by correct answers. It learns from labeled examples. If there were no examples, it would be unsupervised learning. We will mention this. We'll mention this right now. Now, in a more formal view, we would have, I've written this anywhere. Let me write this here. We would have n examples. This would be the size of our data set. And each example, now we're going to do some mathematical notations here. Each example, each row xi is an element of an RD set, which is a d-dimensional vector, and our target to solve is yi. So n is the number of rows, and d is the number of features right here. If we have 1,000 people and we have 5 features each, or 4 in this case, we would have n of 1,000 and d of 5. Next type of learning is unsupervised learning. So with supervised learning, we had inputs and correct answers. But with unsupervised learning, we are saying, all right, well, the only thing we have for you are inputs. We don't have any answers. Figure something out. We have no labels, we have no teacher, we have no supervision. And our data set looks like this. And right, put 1. This just means the following. We have, like in the last example, n examples. Each example is just x. There's no y. So instead of, if you remember, instead of having x1, y1, x2, y2, and so on, we just have x1, x2, x3, all the way to xn. We only have feature vectors. We have no correct answers here. The x here is the same as before, a feature vector. And each x could represent a person again. Each x could be, again, a height, a weight, and an age. But the thing is, now we don't know anything about labels. We don't know who's healthy, who's unhealthy, what is spam, what is not spam. We can only see patterns in the raw data. So the goal of unsupervised learning is to create a model that transforms X, all the inputs, into something useful, which is, because this is a definition from the book, it's intentionally vague, because there is no single correct answer. What are we doing instead is trying to discover structure, compress data, detect weird points, find patterns, things like that. For example, we could have a certain algorithm and we can have a couple of customers, customer 1, 2, 3, and 4. And let's say customer 1 buys expensive stuff and visits often. Customer 2 buys cheap stuff and visits rarely. Customer 3 buys expensive stuff and also visits often. Customer 4 buys cheap stuff, visits rarely. We have no labels, but the algorithm itself might notice, oh, so these two customers are forming groups. I can put customer 1 and 3 that are visiting often in one cluster, and I can put 2 and 4 in another cluster. So again, let's go and define a more formal definition of this. So the model will output f of x cluster ID. So instead of predicting a real label, it predicts something like cluster 0, cluster 1, cluster 2, and so on and so on. But these cluster IDs are not given to us beforehand. They are invented by the algorithm. There's also another concept here, and maybe give me this green color. It's called dimensionality reduction. So if our feature vector had information such as height, weight, age, smoker, gender, history of diseases, I don't know, whatever the way we could represent it. And then we can also say things like hair color, eye color, color of pants, color of t-shirt. And let's say 1,000 other features. We understand that this is very, very, very high dimensional. So dimensionality reduction will ask us, can we maybe compress this information into fewer features without losing too many information? And we could. For example, for our specific case of finding out whether a person is sick or not, we can remove the color of the pants and the color of the shirt, because it's not needed, it doesn't tell us any important information. Why we do this? Visualization, speed, memory reduction, we remove noise, things like that. You know, basically, I don't know, let's say you have a shop and you are tracking customers, and most customers, let's say these are the visits. let's say these are sections of 10, this is money spent. And if most customers are here, they come 1, 2, 3 times. And then you suddenly see a guy right here that visited more times and spent more money. You are telling yourself, all right, this is weird. So unsupervised learning can detect this point is very different from the rest. And usually what the model outputs this information as, I don't know, f of x is 0.01, which says, oh, this is very typical, or f of x is 0.95, that says, oh, this is very unusual. It doesn't give us a class. It gives us a score that tells us how unusual, how strange something is, all right? I went through the book. It says here that it won't mention reinforcement learning, so for this sake, I will just, yeah, cut it here. And now we have semi-supervised learning. Right. Semi-supervised. We had supervised learning. We had unsupervised learning. Lots of label data, no label data. So semi-supervised is a combination of these two. We are having a little label data, a lot of unlabeled data, so it's kind of like a hybrid. We do have some examples that are like this: x, x1, y1, x2, y2, but we also have a lot of x3s, x4s, x5, y5, etc., etc. So the goal is still to learn a model that predicts labels, same as supervised learning, but now we also use unlabeled data to help. Right. We are skipping reinforcement learning. Oh, a lot of interesting things are written here. So specifically now, let's mention how supervised learning actually works. That was a small introductory description. Now we are getting into the real meat. Right. Now this is the section where we actually describe how it works under the hood. So the big picture we already mentioned. We collect data. We collect data to numbers. We choose the learning algorithm. We train the model. We use the model to predict. Everything else is details. And as we mentioned, we can walk through an example of spam detection, because we want to classify emails as spam and not spam. And let's say we collect 10,000 emails, and each of these 10,000 emails is labeled manually. So now we have email, text, and label, let's see. But we have a problem, because algorithms cannot understand text, they only understand numbers. So we somehow must convert emails to numbers. I think this is really important, convert to numbers. So what we use is something called bag of words. Convert to numbers. In this specific case, we can use bag of words. And how this works is that we take a dictionary of different words, starting with A, Aaron, all the way to zoo, for example. Let's say it contains 20,000 words. Now for each email, we create a vector of length 20,000. And for each word in the dictionary, if the email contains that word, we are going to put 1. If not, we are going to put 0. If we have a tiny dictionary, if we have something like, let's say this is our dictionary, free money meeting project, and if our email says free money now, our feature vector would become, all right, free 1, money is 1, meeting is 0, and this is 0 as well, the word project. So if our dictionary contains 20,000 words, we basically transformed our text into a vector of size R20,000. And each email is now a point in a 20,000 dimensional space. So our dimensionality is the size of the dictionary. So our dimensionality is the size of the dictionary. I have the 20,000, and then I have X, an element of R of D, or R of 20,000. Now, our labels must look like this. Let's say +1 is spam and -1 is not spam, so that our data set could look like this: x1 spam, x2 spam, but instead of spam we are writing 1 1, x3 -1, x4 1, and so on and so on. So this algorithm is seeing each, actually this training sees each email as a point in a 20,000 dimensional space. And if we imagine 2 dimensions first, we know that points are looking like either spam or not spam. You know, in 2D, if we have, I don't know, wait. Let's say these are spam and not spam. We could just draw a line between them. In 3D, we would create a plane. Let's say this is a plane from this side. Our spams on this side are not spams. In a 20,000 in 20,000 dimensions, we would draw a hyperplane. Now, what's a hyperplane? So the hyperplane is the decision boundary. In 2D, it's a line. In 3D, it's a plane. In D dimensions, it's a hyperplane. And the hyperplane equation looks something like this. Minus b equals 0. This right here is the dot product. This basically means that this is each feature multiplied by each weight plus v2 x2 plus v dimension x dimension. Each word gets importance weight. And for example, the word Aaron right here would get minus 1.5. The word Zulu would get minus 2. The word A would get minus 1. But if we had a word, for example, free somewhere, let's say free would get the weight of 2.3. Basically, spam words are getting positive weights and normal words are getting negative weights. And then this right here is computing the total spam score. And B is just a shift. It moves the boundary left or right. It's something similar to a threshold adjustment. And basically, again, let me zoom out a bit, let me zoom in a bit. We have points where we have where this is greater than 0, points are on one side, and we have another one where points are on the other side. All right, let me stop here. We haven't covered a lot of the book, but I think I'm gonna continue with it. So see you next time. Bye.